Yeah. Let's see. So reminders that there is a midterm coming up on Thursday, tomorrow at noon. I'll be posting it. And you'll have, again, until Sunday night to complete it. And there'll be one more review session on whatever anybody wants to ask questions about tomorrow, 10 to noon in the Math Commons room, which is in Adams Hall, just by where my office is. Any questions about anything administrative related to that or anything else? Okay, there was an excellent question posted. And in the last review session, we were talking about this a little bit. I think it's very important that we understand why this question is the way it is. And it's going to, it ties in very nicely to the things that we've been talking about Monday, continue talking about today. So we'll go ahead and talk about it. This question, not from this, from the review, true and false, practice problems, numbers 12 and 13 down here, where there's these two hypotheses classes and understanding the differences between them and how it affects our in-sample error and our generalization error. So we'll go ahead and work through these two problems today. And there we go. I'm gonna just switched over to a blank sheet right here, so I have room to draw. But it's those problems 12 and 13 that we're talking about here. Where's my cursor? Let's get this thing working. Come on, USB. Yeah, there we go. Okay, so there were two hypothesis classes. This HL2 to 4. And if we draw that out, then there's what that looks like. The individual hypotheses in the hypothesis class look like a series of concentric circles. And there are 4 of them because there's 4 different possible values of the alpha hyperparameter there. And on each one of these things, I believe it was negatives on the inside and positives on the outside. That here, if you're greater than or equal to this alpha, then the hypothesis will return a positive value. But if you're less than that, then it will return a negative value. And so the size of this hypothesis class, there's just 4 things in it. No matter what dimension you're in, the size is 4. Number of elements in that is equal to 4. The other, this is an example of a hypothesis class that we have not explicitly talked about at any point in class. And you're responsible for being able to understand relatively simple hypotheses like this, even if we haven't explicitly talked about it at any point in class. This other one is one that we did talk about. I called it the axis 2. And what this one looks like is so here there's a 2-dimensional problem. You pick one of these 2 axes, and then you label things as either positive on one side or negative on the other, depending on the value of sigma. So here, sine of x sub I, this I is referring to which one of the dimensions that you're looking at. This is a subscript inside of this x variable. Again, the x not bold sub I is indicating that you're at the ith position of that x vector. If it was bolded, then it would be the ith vector in a data set, which wouldn't make sense here. But so this x sub I is referring to this particular x right here, the ith position. And we're using the sine function to, if it's positive, we get a +1. If it's negative, we get a -1. And then this sigma over here can possibly revert that. And the size of this hypothesis class is 2D. because there are d dimensions, and for each one of those dimensions, we can have either positive or negative. In general, when you're trying to compute the size of a finite hypothesis class, you have all the different choices of things over here to the right of the colon. These are the hyperparameters of your hypothesis class, and each one of these is selected from some set, and you multiply the size of all those sets together to get the size of your final hypothesis class. And so we have a result that our generalization error, E in minus E out, looks something like O square root of M over N, like that. So this is not the VC dimension result. This is the we didn't actually name this particular theorem, but it was derived from Hoeffding's inequality. And it's sort of equivalent to the VC dimension theorem, except the VC dimension substitutes the VC dimension up here instead of the hypothesis size. Say it again. The bottom? That is an in down here. So M always referring to, in the textbook, M always referring to the size of a hypothesis class, N always referring to the size of a data set. And so the more data we have, the smaller generalization error we have, the larger hypothesis class that we have, the larger the generalization error is. And so if we make M bigger, we also need to make N bigger to guarantee, using this formula, that we'll have a small generalization error. And in this case, so the second of these two questions down here, question number 13, is asking specifically about the generalization error. I don't provide the formula here, but it's expected that if I say something out in words, that you're able to figure out what is the corresponding formula and what are the interesting corresponding theorems related to that formula. And sometimes I might use the words, sometimes I might use the equations, and you'll have to be able to understand in both situations. But so it's talking about generalization error in this case. Actually, it's saying generalization accuracy, so I'll have to be a little bit careful here. Generalization accuracy being like 1 minus the generalization error. So here's the generalization error. And yeah, and so this second hypothesis class, h-axis 2, is going to have a worse generalization error because the M value up here is larger. It specifically says for large D values, this one is going to be larger. And yeah, so talking about En minus E out, this thing over here is VC theory predicts that it's going to be a larger generalization error. Any questions so far? Yes.
Could you know why the size of axis 2 is 2D?
Yeah, so the question is, why is this equal to 2D right here for the h-axis 2 hypothesis? And if we come back over to the question, so here's the definition of h-axis 2. In general, so this notation here is called set builder notation. In Python, it's familiar, or the corresponding thing in Python is the list comprehension notation. And everything to the left of the colon, all of this stuff right here, this is the elements. Every element of the resulting set has this form right here. But sigma and x sub I are variables that have not been defined anywhere. And so the stuff to the right, the stuff in the green, defines those variables, what they mean. So that's the sigma and the I. In Python, it would be the 4 sigma in this list right here. The colon would be written out as 4 in Python. And so sigma can take on +1 or -1. I can take on any value inside of D. In order to get all possible combinations of those two things, you multiply them together. So sigma has size 2, I has size D. So 2D is the final resulting size of this hypothesis class. First, did that answer your question?
Yeah.
Oh, yeah, John.
So you said that h-axis 2 or like larger generalization.
Correct.
But the answer to this
Let's see. So the T algorithm on the respective hypothesis classes. Then for learning problems with large D, VC predicts that will have better generalization error than G access to. Yeah, so here, so GL24 right here, this one is going to have smaller generalization error. GL24 will have smaller generalization error than G-axis 2. That's the thing that we claim. Better generalization accuracy is also the same as better generalization error. So large VC predicts that GL will have better generalization accuracy too. That should be true. If it says false in the LaTeX, then I believe that's a typo unless I'm missing something about one of these symbols here. So one of a lot of tricky things about this midterm. One is just the material is abstract, difficult to understand because it's abstract, but also because in a question like this, there are so many symbols that keeping track of everything that's going on is difficult to do. So I could have made a mistake here. Let me just double check. So there's our two things. G and G are corresponding to the T algorithm. The important thing about the T algorithm is that first of all, it only works for finite hypothesis classes, but T will compute the empirical risk minimizer. So we can, for a finite hypothesis class, we can exactly compute G equals the arg min over H in capital H E sub n of H like this. And yeah, so for finite hypothesis classes, we can exactly compute this. For infinite hypothesis classes, we needed to do gradient descent, second order gradient descent, stochastic gradient descent, one of those things to get an approximate computation. But here, these are finite, so we can compute them exactly. And so we're asking about the exact theorem. Then for learning problems with large D, VC theory predicts that GL24 will have better generalization accuracy than G axis 2. So GL24, again, coming from this one, which has the smaller value of M. Smaller value of M does lead to better generalization accuracy. So this one should, in fact, be true. If it says false, that is a mistake. Any other questions about 13? We'll go on to 12 here in a second. Okay, the key difference between 12 and 13 is that it's talking about the here the in-sample error rather than the generalization accuracy. And this is confusing for a number of reasons. Again, one, you just have to pay very close attention to exactly what the question is asking on all of these problems. It's also confusing here because we said as a heuristic that people use in practice, smaller, so I'll write this out, emphasizing heuristic here. The heuristic is that smaller classes have higher EN. And that's, we'll formalize this here in a second to see exactly what are the situations that it exactly holds and doesn't hold. But it's important that this is just a heuristic and not a fact that you can rely upon. And over here, it's specifically talking about being guaranteed to hold. And so we can't rely on the heuristic for things about guaranteed. And what I'm going to do is I'm going to create two data sets now. These two data sets will, one data set will be custom designed just so that it works well on this hypothesis class and fails on this hypothesis class. And the other data set will be designed to work well on this hypothesis class and fail on this hypothesis. And so we'll be actually providing a counterexample to this problem showing that it must be false. So the two data sets that we'll consider here are, we draw out two axes again down here for the two different data sets. And on the first data set, we will get the pluses and minuses right. I'll put a minus point way out here. And so this, I'll just do a dotted line like this to indicate that that's the 4 location. So that's the largest of the circle hypotheses that we can select. And this minus is greater than 4 distance from the origin. The L2 norm of this X value is greater than 4. And so there is no hypothesis class in the L2 4 hypothesis. There's no hypothesis in that hypothesis class that can classify this as a negative sign. In order to do that, our alpha value would have to be greater than this distance, and we're just restricted to alpha being smaller than that. So the En of G L2 4 here is going to be equal to 1 on this very small trivial data sets. In contrast, for the axis points, it's very easy to select. There's multiple hypotheses that can classify this one accurately. We can just select to use this bottom axis and put the negative things on top. And if we do that, then the En of G axis 2 will be equal to 0. So for this data point, if or for a data set that somehow had this property of all the negative things being very far away from the origin, it would clearly be better to use the axis 2 hypothesis class than the L2-4 hypothesis class. But that's not the case for all possible data sets. That if we have another data set that looks like this with a whole bunch of positive things near the origin, I'll put 1 in each quadrant like this. And all those things are going to be less than a distance 1 from the origin here. Then our En of GL24, that is equal to 0. And in fact, all of the hypotheses in this hypothesis class will correctly identify all of these data points and give us a 0 error like this. In contrast, though, if I pick the axis hypothesis class, then the in-sample error on that, En of G axis 2. Here, no matter which hypothesis I pick, I have to get exactly half of the data points wrong. But if I pick this vertical axis, doesn't matter whether I put the positives and negatives on which side. Same with this horizontal axis, doesn't matter if I put the positives and negatives on which side. I'm going to get exactly half of them right and half of them wrong. So this error is going to be 0.5 over here. And so because of this, we've specifically shown 2 different data sets that show that En of one of these values cannot be always less than En of the other hypothesis class. And so the question must be false. Okay.
Just like a technical thing about like the L2 class, but then either side of each like value circle can be either side be positive or negative, or
yeah, so the question is, so looking back at the picture, on the picture here, I labeled negatives on the inside and positives on the outside. And the question is, can we reverse that? Can we have positives on the inside and negatives on the outside? And the answer is that the way this is written, you cannot do that. The way this is written, so these square bracket things, again, evaluates the contents if it's true to be positive 1, if it's false to be negative 1. And so if we're greater than alpha, then we're guaranteed to be positive. It must give out a positive over here for large things bigger than alpha. And if we wanted to be able to switch it around, then what we would do is we would add the sigma variable out front over here, and then also adding the sigma contained in. +1, -1, like that. If we did that, then we would be allowed to switch the positives and the negatives around. And so then if we did that, then the particular example that I have down here would not work anymore. It's not, then we would be able to classify this as a positive. But if I added another negative data point way down here, then we would still be in the situation where there's no way that the circle hypothesis class can correctly classify both of these two things at the same time, but the axis hypothesis class can. Did that answer your question? Good question. Any other questions on this problem? Oh yeah, one last thing. So what is it? What is the actual thing that makes this heuristic true? What do you actually have to have in order for this heuristic to be true? You actually have to say that one not only is, let's see, I'll put it up here. So smaller hypothesis classes, heuristic, the actual true thing, fully true thing is that if H1 is a subset of H2, that will imply that En of G1 is greater than or equal to En of G2. Being a subset is a particularly strong statement about H1 being smaller than H2. And that's what you actually need in order to get this implication over here. Any questions about this problem? Okay, then we're going to move on to, again, talking about this model zoo set of notes. And one of the things to keep in mind as we're talking about this is, so we're going to be talking about the VC dimension of many, many different hypothesis classes. And that gives us the ability to tell us what the generalization error is going to be. But it does not tell us, again, what the training error is going to be. It does not tell us anything about the in-sample error. It gives us this heuristic guide that we'll see here in a little bit, that the decision tree has a much higher VC dimension than the linear hypotheses classes. And so that gives us a sense that probably for complex data sets, we can get E sub n to be smaller, but it doesn't guarantee that in any way. Because it's not strictly a superset. And one of the reasons people like these pictures of decision boundaries is it helps give you a little bit more sense of when different hypotheses classes will have lower training errors versus higher training errors. So we have talked about the neural nets here, that they have one of the things that we've sort of seen. We'll see here another example in a little bit. They have smooth-ish decision boundaries. And so if your data is like, I don't know, you think it's a little bit smooth somehow, then neural networks may be a good thing to use. These decision trees, this AdaBoost thing, they have very like sharp corners in their decision boundaries. And so if you have reason to think that your input data has sharp corners, those two things good to use. These RBF or Gaussian processes, very, very smooth boundaries. And so if you have very smooth data, then reason to think that those would be good. All of these models are going to have various things that control their complexity, that control their VC dimension. And so we can get a decision tree with a VC dimension basically the same as any neural network we want. And so why would we choose a decision tree over a neural network or vice versa? It's not because of the generalization error. We can control the generalization error for anything using the VC dimension, but it's with the in-sample error might be better for decision trees than neural networks on your particular problem. Just like on your particular problem with these two hypothesis classes, the in-sample error might be better for the circles or the axes, just depending on what your data actually looks like. So we started talking about the linear and quadratic models. The main takeaway here was that in scikit-learn, for example, there's dozens of these linear quadratic models, and they all have the same VC dimension properties. They all have the same generalization error. But either logistic regression or SVM actually is going to minimize the EN. All the other things don't directly minimize your in-sample error. And so if you're doing something linear quadratic, everybody always uses logistic regression or SVMs. There's a lot of other things here. Nobody uses them. Where do we go? Here we go. Then we started talking about the neural networks, the multi-layer perceptron, and the main takeaway from this in terms of solving problems is going to be how the VC dimension grows with different properties of things. And I want to take another look. We use this to visualize some of our decision boundaries of neural networks before. And we specifically looked at this circle sort of data set right here. And so again, the way this visualization is working is right now I have 0 hidden layers. If you have a multi-layer perceptron with 0 hidden layers, that's the exact same thing as logistic regression. And so if I run this, I'm going to get just a straight line decision boundary. And so I can't do well on this data set right here. The first tool that we saw and that you're responsible for on the midterm is that we can use something like the polynomial kernel. The polynomial kernel adds features directly to the input over here. These features correspond to the second degree polynomial. This is the squared x value, the squared x2 value, and then x1 times x2 down here. And if we were to run that, now we can exactly classify this data set. The cool thing about the neural network, though, is that it's like automatically learning our feature transformation for us. That's the actual way that people think about neural networks, is we don't think about in terms of the brain or anything like that. That's all just hocus pocus to make the muggles want to give you money. But we actually think about it as learning these things for us automatically. And so if I'll take these 3 features away, add a couple more features over here, see if that'll work for us. And now this has sort of automatically learned for us that something sort of like the polynomial feature map is going to work well on this data set. Question?
So if we like set a certain amount of hidden layers in the is it guaranteed this to at some point give us exactly the same results as the polynomial kernel?
Good question. So one thing that I don't think we explicitly talked about last time, maybe we did, I guess we did, here's this universal approximation theorem for neural networks. And that's that any one layer neural network, any one layer MLP multi-layer perceptron. So that means that this one is a 2-layer multi-layer perceptron here because there's these 2 input features here. But all I need is one of these features. If I make that big enough, then I'm guaranteed to be able to drive my training error down to 0. And so in this case, there we go. That these 8 features right here drove the training error basically down to 0. And if you make this big enough, then any feature map that you had over here that you explicitly constructed, the neural network will automatically relearn for you. The disadvantage of the neural network, let's say, yeah, so that's the advantage of it, and it's a strong advantage that we can learn any feature map that we want. The disadvantage, though, is that it has a very large VC complexity, and so it's very easy to overfit on things. Yeah, I mentioned, so yeah, again, the right way to think about these multi-layer perceptrons is that we're learning these features automatically. These things down here are the visualizations of the features that have been learned by this neural network. So instead of having just vertical and horizontal lines, we have all of these things together. And if you take the weighted sum of those, then you get this circle-ish shape. And the more we had, the more exact the circle would be. No.
Can you explain like the data methods? You know, how that's different from I'm a little confused about like what adding in the layer.
Yeah, so the question is, what does adding a hidden layer actually do? And the verb do is one that gets thrown around a lot, and it, I don't know, hides a lot of different things inside of it. One of the things that students very often want, and that we're not doing it all in this class, is I want to know how to implement this. Like, I want to know exactly what are the electrons in my computer doing when I press this play button up here. And we're not going to be talking about that. One of the reasons for that is that this is a data mining course. Data miners don't implement these algorithms, we just use them. Another reason is that when I talk to people at like these conferences I go to, and I ask them, what are you looking for when you're hiring students? And I specifically ask them, like, does implementing something, do you look for that when you hire people? And half the time the answer is, I've never implemented that. So I would never expect people I'm hiring to have implemented that. So yeah, the important things, the things that you really have to know in order to know to use them are like, how is it actually going to affect the generalization error? And that is captured by our definitions, our theorems down here about what the VC dimension is going to be. So I'll go over these in more detail, but this, basically everything that's on the screen right now is the thing that's really the most fundamental thing that like when I think of what does a neural network do, the way I interpret that verb do is it provides these particular guarantees on my generalization error, which other algorithms provide different guarantees. So yeah, the important answer to the verb do is, what is the guarantees that it provides you? Another way to answer the do besides the implementation and the guarantees is something sort of in between that, which is like, what does the hypothesis class look like? We know that all of the models somehow have a hypothesis class and an algorithm that optimizes that hypothesis class. And so one way to interpret what does a model do is to interpret what is the hypothesis class that it is optimizing over. And the right way to think about the MLP hypothesis class is as a generalization of our perceptron hypothesis class. So this was our perceptron hypothesis class right here with the phi feature embedding right here. And what does the MLP do? Well, it lets us actually learn this feature embedding automatically by, you don't provide it, you don't say I'm using polynomial kernel of degree 2. Instead, you say I'm using this function right here as my feature embedding, and I'm going to learn this W1 as well as this W up here. That's the one layer perceptron. The K layer perceptron or the I layer perceptron is then let's repeatedly apply feature embeddings, and this is just a recursive formula that illustrates that. And so that's another interpretation of what does the MLP do? Well, this is the hypothesis class, and it somehow selects a hypothesis from this class. Last interpretation is, again, each of these pictures right here is supposed to be representing like what is the value of that particular feature. So if you hover over here, the orange things are negative, the blue things are positive, and so the X feature that's what it looks like. The farther to the left you go, the more negative. The farther to the right you go, the more positive. The way that phi function is creating new features for us is it's making linear combinations of these other things and then providing a threshold on that. So that it's like it's using logistic regression or a perceptron to learn more of these intermediate representations. And these are what those intermediate representations happen to look like for this problem. And so then it combines all those together in one last step and lets us approximate the circle, which would be the ideal representation for this particular problem. And yeah, so there's lots of answers to that question of what does the MLP actually do? Very likely that none of those answers feel satisfactory to anybody. And I guess part of the difficulty of the data mining class is that level of abstraction. And the fundamentally most important thing of what does it do is it provides, I think, yeah, if there's one interpretation that you should take away from this class, it's that it provides these guarantees on the generalization error, whereas other classes will provide different guarantees on the generalization error. I don't know if that's helpful or not, but that's the answer to the question. Yeah. Oftentimes in a class like this, and this was certainly when I was learning this material, that like when I first took the class that introduced like DC dimension and all these things, I basically felt like I had no idea what was going on at the end of the course. And it was 3 subsequent classes later that all of that stuff finally like clicked. And yeah, so you might not have the like enlightening aha moment in this course, but hopefully it's preparing you to have that aha moment at some point. Is that a question, Alex?
Yeah. So the I is the number of layers in our neural net, and what is the number of neurons per layer? Is that the matrix A or?
Good question. So here on this version of the phi function, it's using this A as the matrix that is the parameters to the neural network that we are trying to learn. This I here is the number of layers. So in particular, if we have a K layer neural network, we would call it with phi sup K, and then it would recursively go down until we get to this base case where there's no more calls to this phi function. So that's the number, this up here is the number of layers that you have left. And then each one of those A sub i's has a pair of dimensions associated with it. And so if you unravel, again, this phi sub I, you'll get something that looks like this. So this would be a depth 4-layer MLP right here. And in order to make this well-defined, in order for it to make sense mathematically, each of these A matrices must have dimensions that somehow match the matrices before and after it. So this A4, this D4 over here, D prime, and then D3, D3, and D3 match each other. D2 and D2 match each other. D1, D1 match each other. And so because these things here, they match each other, when we're describing the neural network itself, we don't repeat them multiple times. But here we would say that D0 is the input dimension. That's the dimension of X. In our picture over here, D0 is equal to 2. And then D1 over here, that's the dimension of the output of the first layer, the number of nodes in the first layer. If we came over here, the number of nodes in the first layer is 8, so D1 would be equal to 8. The matrix that sits between this and this over here is a 2 by 8 matrix, and so there's 16 total values. Each one of these little lines right here is supposed to represent the value in the matrix that maps this thing over here onto the input of this thing over here. And so there, if you were to count them all up, there'd be 2 times 8 is 16 of these lines here. And then there's only a single output of this neural network going into plus or -1 over here. And so our final D prime would be just equal to 1 in this case. Did that answer your question? Okay. So one more, let's see. So there's a bunch of different data sets over here that it's possible to play around with. This is another data set that can be solved with the polynomial kernel. So let's just do that real quick. And easily solved second degree polynomial. This one over here, just a linear data set. You don't need the polynomial kernel. And if you use the polynomial kernel, you can see we're overfitting it a little bit. We should probably have the straight line separating it, but we're getting a quadratic instead. And so changing this, restricting our model, selecting specifically a hypothesis class that is a subset of the previous hypothesis class, we get a better generalization here with the exact straight line. This last one down here, the spiral thing, if I had the right features, then this would be a very simple thing to learn. That you can see all these, it's just like a line that's kind of been twisted up like this. And so if I were to unflatten this into a straight line, then all I have to do is learn what is the right spot to start going from blue to yellow. The polynomial kernel is not able to do that though. And if we see, we get something like this, our training loss and our test loss remain really bad. And I could maybe try to like work out mathematically what is the right feature that's going to give me this. In this case, since it's two-dimensional and possible to visualize it, that wouldn't be too bad, although it'd still be kind of a pain in the butt to figure out like what the mathematical thing is for this. If it was higher dimensional, something you can't visualize, then you'd have no hope of just looking at it and seeing what is the right formula. And so that's where something like neural networks can come in. That's, there we go, something like this. And we'll do this and we'll see that it's going to try to learn the features for us automatically. Let's see, this one's not working. One thing that I didn't, oh, there we go. It's just getting really slow. Somehow getting a little bit better. Nope. These neural networks are non-convex. And so sometimes if you restart them, you can get to a better solution. See if that works. Maybe not. Let's add some more things here, see if that helps us at all. This was converging in my office. Let's make this smaller. Okay. A little bit more attempts at things. Let's get even more complicated. So we weren't actually fitting the function here to begin with at all. So I'm making the model more complicated now to try to reduce my in. I'm making my VC dimension worse, but that's okay. Looking up here, I can see that the slope of this, it's still getting a little bit better and better as it's training. So, and if I look down here, I can see that things are starting to change. That's kind of starting to loop around here. That orange is maybe coming in. Hopefully it'll start capturing this. See, these errors are slowly going down and down. If you look internally at these are the, again, the internal features that we're learning. They're getting more and more interesting shapes. They always start off as just like linear things, and then you get these weird shapes and more interesting as you go down. And now you can see that it's starting to fit that pretty good over here. And if I let this keep going, it looks like it would keep learning for a while. It is very weird, yeah. But that's like the intuition about like why you might want to use a neural network is that you don't have a good idea about what is the best feature map, and so we'll just try to learn the feature map from the data. And actually, you can see that our loss is down here. Training loss is almost down to 0. Test loss a little bit bigger than that. Again, that's the VC dimension. I made a particularly complicated network down here. If I wanted to try to reduce this test loss, then the right strategy would be to reduce the number of layers or the size of those layers while still maintaining the right amount of complexity to get the right training loss. Any questions about any of that? Yes.
You mentioned that like, what, they're non-convex, so what does that have to do with, and they're like, you can start training it again?
Yeah, so let's come back over to the notes a little bit. Somewhere, here's this fact right here. The optimization problem of neural networks is convex only when the activation function is the identity function. If you do plug in the identity as the activation function, you get the exact same thing as logistic regression. But everybody, what people actually use in practice is always the ReLU function. But anything else besides the identity, also non-convex. And so if we were to plot out what the loss function looks like, it would be, I don't know, people do lots of research just trying to figure out like, what does the loss function look like? But it looks something like this with a whole bunch of local minima spaced all over the place. And so if we were to start your optimization right here, you might end up like, oh, I'm right here, but I really want it to be right down here. And once I'm down here, I can't get down here. One of the reasons, so for neural networks, people always use stochastic gradient descent. They never use actual gradient descent. And one of the reasons for that is because if you use actual gradient descent, as soon as you like hit one of these local minima, of which there are a lot, then you're stuck here. But if you're stochastic gradient descent, you always just have like random moves that you're making. And so sometimes those random moves will take you out of those local minima and tend to get you more towards the better area. But it's always the case that if you're just not converging to a good answer, maybe if you restart your problem with different random seeds, different initial conditions, instead of starting far away, you might start closer to the optimum and get a better result that way. That's not the true for logistic regression. And this, that if no matter where you start from, no matter what your initial random state is, you're always going to converge to the same result for logistic regression. Okay, good questions. So yeah, so we worked a small problem with neural networks, just plugging in some of these values into the VC dimension formulas that we had to figure out which versions of the neural networks are going to be more or less likely to overfit. There's this alpha parameter right here, this alpha in the scikit-learn. We haven't talked about all that, and I'll talk about it really quickly, but for all of these models, there's going to be some parameters, some hyperparameters that we're not going to talk about. And my expectation is that you are able to go to the scikit-learn documentation and figure out what that parameter is doing from the documentation and answer the questions appropriately. So let's see how to do that here. The alpha parameter, if we come over here and here we go. So this is the documentation for the multi-layer perceptron right here that I'm at. So MLP classifier, and talking about the alpha parameter. And alpha is just L2 regularization. And so as you make alpha larger, you're adding more regularization. And it has these visualizations down here in particular that if you make alpha really large, you're making your model basically more linear. And if you make alpha really small, you're or all the way down to 0, you're getting more of the power of the ability to fit tightly different sorts of data sets. So better E sub in for low alpha, but also worse generalization. And so down here, large alpha improves generalization. Another way of saying that is it adds regularization. And between these two models up here, we said that this one, it has smaller numbers, but the depth is larger, and the fact that some of these numbers have to get squared makes this model much, much more complex than this model. And so for choice A, the one with the layers equal to 10, 10, 10, would need more regularization. because it has a much higher VC dimension. And again, my expectation, so we've talked about regularization, how that affects problems. We've talked about the VC dimension, how that affects problems. There are other hyperparameters associated with the MLP and all these other things that we're talking about that we're not talking about in class. But my expectation is that you'd be able to look into the documentation, figure out what that hyperparameter is controlling, and figure out how you should adjust it for a particular problem using an argument like this. Yes.
Can you explain why the list 10-10-10 has a higher VC dimension?
Yeah, the question was, why does the list 10-10-10 choice A right here have the higher VC dimension than choice B here at just list 100? And we went through that pretty quickly at the end of the last class. But there are these two theorems right here, which give us bounds on the VC dimension of neural networks with different characteristics. And these theorems are admittedly extremely complicated just to sit down and read these theorems. We're certainly not going over the proofs of these theorems at all. I think I actually have so this bottom paper right here, theorem 3, published in 2017, fairly recent discovery that these are the bounds on the VC dimension of a ReLU neural network. In class, we'll almost certainly be talking about ReLU neural networks since they're the most popular. So this is the most important theorem here to work with. This is the actual paper, just bring it up to highlight that it's 16 pages of super dense technical math. I have not made any attempt to try to understand this paper. My guess is that there are less than 10 people in the world who have read this paper. But there are thousands of us who actually rely on this result and make our decisions based on this result. And so this, yeah, it's maybe a very different than other math-heavy classes where the point of other classes is to prove results. Proving something like this would result in a PhD being awarded. So we're not going into proving these things. That's a really hard thing to do. Instead, we're going into the why do we care about them, and so the why do we care, we picked these formulas over here. We plugged in the numbers right here to get the VC dimensions, computed that the top one had a VC dimension of, I don't think we even bothered to write the number. It was just this whole thing. It's I don't know, 10 to the 10th or something. Very large VC dimension for part A, but down here, the VC dimension was only 10 to the 5th, only 10 to the 5th. And so much better generalization down here than up here. That answer your question, Chuck?
Yeah, so because the E is higher, it's bounded by the E.
Exactly. Great questions. Any other questions so far? Okay, we will, let's see. So after this notes packet, this is the most, the theory stuff in the course will be peaking at this point, and we will be getting more practical, more programming assignments, more solving actual data sets, problems. And when we do that, we will talk about neural networks in more detail from a practical perspective, and you'll be solving some problems with these. But at this point, this is the last for neural networks, and on to the next model, decision trees. Yeah, one last thing actually that I wanted to say, at the very beginning of class of the semester, many weeks ago now, we started off talking about this particular problem right here, where our input was a bunch of numbers, and we wanted to figure out how to write a program that's going to read these numbers for us. And what we said was or what we did in class, we actually trained a bunch of models in class at the very beginning, and all these training operations just take like 3 lines of code right here. And those 3 lines of the code are the same for every different model. It's the same for logistic regression, same for multi-layer perceptron classification, same for decision tree classification, with the exception that you have to pass in whatever hyperparameters you want to that model. And so this, yeah, what we're talking about right now probably feels like totally unrelated to code, very abstract, very mathematical, but it's actually like exactly what we were doing the first day of class. Now we have tools talking about the VC dimension to understand their generalization errors and these different trade-offs. And so as you're in practice working on these problems, deciding which one of these things to use, which one of these 3 lines is going to be the best one to do, you don't actually have to run it to figure it out. You can run it, but sometimes running it can take hours or days, and so that's slow. We can use our theory to just zero in on like what seems like probably good or reasonable things to choose. So that's why we're talking about this. So decision trees. As implemented in scikit-learn, lots of different variations of decision trees that are used in practice. But this one right here is pretty representative of all of them. As the name implies, they have a sort of tree structure that you make some simple decision. So you have a simple if statement, and then if yes or no, then go on to some other simple if statement, and then yes or no, and so on. And each one of these branches eventually will give you like a label associated with it. So +1 in these cases and -1 in these cases. And I wrote simple if statement in a very generic form because simple is, I don't know, up to my definition of simple seems to be different than students' definitions of simple. But what this decision tree classifier actually implements is you look at an individual feature, one feature at a time, and check to see if it's greater than or equal to some threshold value. Each one of these decisions right here, again, only looking at a single feature at a time. You're never looking at like a combination of features. The feature direction of the inequality can be either way, less than or greater than. We could have the features be the same for subsequent levels, or they could be different. It doesn't really matter. The sort of situations where we're going to have good training error. Let's say we have a data set that looks something like this, a bunch of pluses in this like very boxy pattern, and then minuses over here. This is a good situation for decision trees. The tree up here would be able to implement this exactly with 0 training error. And this would be a bad situation for something like linear regression, even with no matter even with a polynomial kernel, this would be a bad situation. That very hard to get like these exact straight corner lines in logistic regression. So I'll say that's good for DT for decision tree, bad for logistic regression. Another example of a data set would be something where there is a lot of correlation between the positives, like what the actual decision boundary looks like, but it is a straight line like this. A decision tree can't, at least as implemented in scikit-learn and in the vast majority of situations, a decision tree is not able to take advantage of two different dimensions at the same time. And so a decision tree, in order to implement this, would have to be like a jagged line like this. So it would be a relatively deep, complicated tree. And so that's bad for the decision tree. But this can be exactly represented as with a logistic regression. So good for logistic regression. In advance, knowing whether your data has sharp corners inside of it or whether it has like these smooth relations. Like, I don't know, small things you can visualize, large things you can't visualize. So you don't really know in advance, but that's the intuition about when decision trees are good versus logistic regression. And this is all in terms of their E sub n. It's a super high level description of decision trees, but any questions about that?
I have a question about the drawing above.
Yeah.
When you have two different statements, the alphas need to be
Yes. So yeah, I should subscript those just to indicate, yes, they are different thresholds. Yeah, so for all these models, we want to have some sort of intuition, even if it's a little bit vague about when they're good for their training error. And then we'll talk about the VC dimension to give us bounds on the generalization error. And so we'll get to that here in a second. This fact two, first of all, so in practice, these days, actually the only times that I see decision trees being used are on medical applications. Doctors really like decision trees because they're really easy to memorize and to evaluate in your head. Logistic regression is also very simple, but doing a bunch of multiplication in your head is hard, and doing a bunch of if statements in your head is easy. So doctors, whenever they're telling somebody they have a certain disease, they're just evaluating a decision tree in their head. That decision tree was probably learned on data and not just like created out of thin air. And I don't know of any other situation in the world where people are currently using decision trees today. Decision trees have a universal approximation theorem. So if K is the number of nodes in our decision tree. So coming up here, K is the number of decisions that we're making. Then as the number of decisions goes to infinity, then our training error goes to 0. So even on like the bad data sets that look like this, if you just have an infinite number of K, like an infinite number of decisions that you're making, you can make this line arbitrarily close to a straight, smooth line. It just requires a very, very large decision tree to do that. Theorem 5 here is our VC dimension. And the VC dimension of binary decision trees is bounded by essentially the number of nodes in the decision tree, but also times this log K times D factor right here. The K inside of here, no one cares about. No one cares about the log K because the actual K over here totally dominates. So who cares about log K? But this D over here is extremely important. If you remember from our linear hypotheses, they have a dependence on D that is linear. And so if we have a lot of dimensions, again, I consider a problem with 10 to the 9th dimensions to be like moderate in size, maybe even small in size. And so something 10 to the 9th is going to result in a fairly large VC dimension for a perceptron hypothesis class. But for the for the decision tree hypothesis class, it's still like very, very small VC dimension. So this is particularly good. Decision trees, DT, good VC dimension when D is large. Are there any questions about that? The problem with decision trees is that we have this linear dependence on K over here, a linear dependence on the number of internal nodes. And if your data set in any way has these decision boundaries that are dependent on two different things at the same time, then you need a lot of internal nodes in order to get that. So you'd have a very high VC dimension to match a problem like this. Even if it's everything square, then you have a very low VC dimension. An immediate corollary to this statement up here is that if so J is the height of a binary decision tree, then your VC dimension is exponential in the height. So this, at first, maybe doesn't seem like it's too bad of a dependence on K over here, but really people usually talk about the heights of decision trees, and we have an exponential dependence in terms of the height over here. Any questions on that? Okay, this problem 4 has a bunch of different hyperparameters that are important to decision trees and how they affect the VC dimension. We're specifically asking about the VC dimension here. And we'll go over a couple of these, but you're responsible for all of them, figuring out how do they affect the height of a decision tree. This first one, criterion, if we come over to the documentation for decision trees, go away Zoom. Actually, since we have this picture up right here, you can see that, so here's the decision boundaries of decision trees on some particular problem. And you can see this effect of like lots of square sort of edges. And so if that's good on your problem, then you'll have a low tree. Otherwise, you'll have a large tree. Where are you? Decision tree classifier. So this first one, criterion right here, this has actually no effect on the number of nodes in your tree. This just determines actually what are the values. What criterion selects is what are the values of alpha that you should be using for your decision, and what are the value, which dimension should you split on. And so criterion will affect your training error. But no effect on VC dimension. And by implication, no effect on the generalization error. The maximum depth, come over to the documentation, maximum depth, the maximum depth of your tree. So by making that smaller, making the maximum depth variable right here, making that smaller, you'll make this J variable right here smaller. J is the height, equivalently depth of your decision tree. Making that smaller will reduce your VC dimension by quite a lot. And so reducing max depth makes the VC dimension go down exponentially. Exponent, do I have room? Exponentially. So this is a very important parameter for controlling the generalization of a decision tree. And so then again, my expectation is that you'll be able to go through, read the documentation for these other things, figure out how it affects these parameters up here, make it bigger, smaller, no effect at all, and and then determine the generalization error based on that. Any questions about that? Okay. Just a few more minutes left, so I want to highlight some quick things. These notes, I'm not making you responsible for the runtime complexities of anything, just the statistical complexities of things. But scikit-learn does have information about runtime complexity inside of it. It does not actually anywhere contain information about statistical complexity. I'm not sure why. But so the neural networks, very high runtime complexity. Come over to decision trees. Actually learning the optimal decision tree is known to be an NP-complete problem. So it is an open problem whether we can exactly find the best possible decision tree for any particular problem. In practice, nobody tries to find the best possible one. They just find an approximate one. And so here's all the various runtime guarantees of what's actually implemented inside of scikit-learn. Again, you're not responsible for knowing these things, but at some point you will be building some decision trees, and it will be helpful to have an intuition about these things. In general, choices that make statistical complexity go up will also make your runtime complexity go up. But there is one thing inside of scikit-learn's documentation that is 100% wrong. I'm not sure why they state this right here. I almost made a pull request this week while I was thinking about things to fix this, but I thought it would be better for all of you if one of you wanted to make a pull request and then talk to your future employer saying, oh yes, I am a contributor to scikit-learn. But this first statement right here, it says, decision trees tend to overfit on data with a large number of features. And that's 100% false, provably so, because the VC dimension is logarithmic in the number of features. So if I have 1 billion features, I only need a logarithmic number of more data points. And so it's just not true at all. What they're trying to say something else about how for more complicated problems, you need a larger depth decision tree. You need more internal nodes, and that results in more overfitting. But the actual number of data points has a very, very negligible effect. And decision trees are actually very good on problems with a large number of data points. That's everything for us to talk about decision trees. We have just a couple more of these models left that we'll get to next week after the midterm. But if anybody has questions about this or midterm related stuff, happy to stick around after class. Or again, we have the last pre-midterm review session tomorrow, 10 to noon in the Math Commons room. This is a good place to stop for today though. So good luck on your last midterm studying.